This video is the first of a few what we're going to call optimization type problems. And so we're going to talk about a few things in here, but we'll just get into it. It says you've got a 10 by 12 inch piece of cardboard that you will make into an open top box by cutting a square out of each corner. What's the maximum volume possible with this size piece of cardboard? So what we're going to be doing, it says we're going to cut out a square out of each corner, and it's going to be the same size square. And the original sheet is 10 inches by 12 inches. And so when we do this, it's going to end up looking something like this. So these yellow things in the corner, these are going to be cut out. And what we're going to do to make our lives, kind of give this an equation here, is we're going to call each square that we cut out, we're going to say that each side that we cut out is just x. We'll just choose some variable. X tends to be a pretty common one. So what we're doing is we're cutting out an x by x square out of each corner. And what's going to be left over, I labeled these flaps that are going to get folded up. So there's going to be 4 flaps that we fold up. And this is an open top box. It says that in the description here. It's an open top box, so there's no lid on this box. These flaps, A, B, C, and D, are going to be folded up. And so since this was 12 inches for the length and 10 inches for the width, we're going to try to figure out what are the new length and width of this folded up box going to be. And so the folded up box is going to look something like this, where flap A is going to be folded up. Same with B, C, and D. And you can see that A and C are across from one another, and B and D are also across from one another. And so side A was 12 inches, but then we cut off 2 corners. And so it's 12 inches, but then we're going to subtract off. How much did we cut off? So think about that for a second. How much did you cut off of that 12? And so what we did is we cut off an x out of each corner, so it'd be 12 minus 2x. And once again, so this is kind of the tougher part to understand, is we cut off, let me kind of do some erasing to re-explain here. Let's get rid of this stuff as well. And so what we did is on that side with the 12, we cut an x and an x off there. We also did the same thing on side B and side D. We cut off x as well, but we cut off 2 x's, and so that's why it's 12 minus 2x. So then likewise, with this D side right here, we had 10 inches, and we cut off 2 squares, so it would be 10 minus 2x. And then what we're going to need, it says, what's the maximum volume? And so we need to figure out what is the volume. And so the volume of any box, something you learn very early on in math, is length times width times height. Well, we have an expression for the length and width. For the length, we've got 12 minus 2x. So 12 minus 2x. And the width is 10 minus 2x. So we have the volume formula. Now we just need to figure out what's the height. And so what the height is it's just going to be x. And why is it x? So think about that for a second. If you're not sure, pause it and think about, how did I come up with x there? And so if you've thought about it and you're thinking if you're right or not, you notice how this part here that I'm kind of shading with C, we cut off x off of C. Whoa, that's a terrible. That is not what I wanted. Back up. Oh man. All right, I gotta find those again. Sorry about that. There we go. So what I meant to do, I'm going to erase that circle. I had a bad circle and a crazy set of undos messed things up. So anyway, we cut off x off of side C, and so when we fold that up, that's going to be x tall. So when we do length times width times height, the height is going to be x. So the volume is this strange, funky formula right here. what we want to do is we want to figure out what's the maximum volume. And so what we can do is we can just plug that into a graphing calculator. In this case, I'm going to plug it into Desmos, and we're going to figure out what is the maximum. And so let's swing on over to Desmos here. And I'm going to type it in. I'm going to hook up my keyboard here. And so we're going to do 12 minus 2x in parentheses. You do not need to multiply this all out because Desmos can do it for you. And then we're going to do 10 minus 2x. And then we're going to do times x. And so I've got this third degree polynomial. And if you notice, I have a minimum over here, but I'm not looking for the minimum volume. In fact, you can't have a volume of negative 5.5, so that one doesn't really matter to us. So I'm going to zoom out here. Let's see if I can do that. Come on. There we go. So there's a maximum right about there. So at 1.811, the maximum is 96.77. Remember, our y value acts as our volume, and our x value acts as how much we're cutting out of each corner. And so if we cut out 1.811 out of each corner, then our maximum volume would be 96.771. So this graph, this third degree polynomial, shows us all of the different x values we could cut out and what the corresponding volume would be. So if I just kind of trace along here, there we go. If I cut out 3.27, let's see if I can stay on there. Of course I can. If I cut out 3.2, it's about 64.5 for the volume. So let's head back to the problem we were doing right there. And so the maximum volume, I'll just write it here, maximum volume is, I already forgot, what is it? It's 96.771. 96.771 inches cubed when x equals 1.811. So when you cut out a corner that is 1.811 inches, you're going to get a maximum volume of 96.771. So some questions that might come up with this are, what are the length, width, and height of this box? Well, you're just going to plug 1.811 back in to the length and width formulas. So that would be, I'll highlight them in pink here, that would be 12 minus 2 times 1.811, and then 10 minus 2 times 1.811. Another very common question that might come up here is, what's the domain of x? And what domain, sometimes we get confused on these vocabulary terms in math, but the domain is just saying, what can x be? The domain of x is, what can x be? What are the possible values of x? Well, x could be anything, right? Except it can't. Because what if x was 10? Could I cut out a 10 out of this corner and this corner and still have something left for that B flap? We can't, because I would cut out 20 altogether, and I only have 10 inches for that flap, and so I can't do that. And so what is the biggest possible thing x could be? Well, the biggest possible thing x could be is 5, because if we cut off 5 out of each corner here, then that whole 10 inches is gone. So x can't be 5, but it can be everything up until 5. For the other side, the maximum x could be for the length side is 6, but it doesn't matter, because if you go above 5, then you have problems on the other side. So the domain, we would say, is between 0 and 5. 0 is less than, I guess you could have it be 0 and just be a flat sheet of paper. Less than or equal to x is less than 5. It can't be 5, because then you'd cut off everything off that one side. So that would be the domain. Okay, a couple other things here. I know this is getting a little bit long, but There are a couple other types of boxes that you might run across in problems like this. One would be like a closed top box. And so let's use the same dimensions just to keep things kind of uniform here. We'll say that this is 10 inches and this side is 12 inches. And so if we have a closed top box, then we have to think about what's this going to look like when we fold it up. And so what I really encourage you to do here is pause the video and think about where are these corresponding flaps going to end up. Like, let's label them A, B, C, D, E, and F. Where's A going to be on this picture? Where's B and C and so on? Where are these all going to end up? And what's the height going to be? All this stuff. So I would encourage you to kind of think about that for a second, and I'll go over it right now. So what's going to happen here, and there's a few different ways you can think about this. So if you thought about it slightly differently than me, but you get the same idea, especially if you get the same volume formula, then you probably did it right. But I think of this rectangle right here as the bottom. I'll just put BOT. So that would be that rectangle on the 3D picture. So then the top would be over here. That would be the shaded in yellow one on this picture. Top. And so A would be over here. Out in front would be E. And on the side would be C. But what's going to happen here, and you might be like, whoa, where are these coming from? What's going to happen is these flaps C and D, when you fold it on top of itself, C and D are going to be right on top of each other. They're going to overlap. Same thing with A and F. So A and F are going to be on the side there. And then B is going to come down on top of E, and so the back flap, the one that we can't really see back here, that's going to be, I'm going to shade it in pink here, that's going to be this one right here. That's going to be the back, I'll say. So the back of this box is going to be that thing that we fold up. So all those dotted lines, maybe I should have explained this earlier, I kind of forgot that. All those dotted lines on this picture over here on the left, all the dotted lines represent where this box is going to get folded. And so the flaps are going to be A, B, C, D, E, and F. We're going to cut out each corner. We'll call those X again. So each corner is going to be, you know, X by X. Maybe that would be a better thing to do instead of putting an X in the middle. So each square we're going to cut out is going to be X by X. We'll do that, X by X. Let's say this side's X. Same thing here, same thing there. And so the height's going to be X again. The length, however, is going to be, this time the long side is going to be 10 minus 2x. That's going to be this side here by E. The short side is going to be, let's see, I'll use orange here. Short side is going to be this one right here. That flap D, this is going to be our short side. And that is not 12 minus 2x. So what it is actually, we cut off 1, 2, 3 x's off of this box. And so it's 12 minus 3x this time because we cut 3 of those off. And then what we did was we folded it on top of itself. So it's going to be half of that. It's going to be 12 minus 3x and then divided by 2. Because, and this is maybe the more challenging thing to understand here, but this bottom and top are identical. They're going to line up just perfectly because we end up with a rectangular prism or a box. And so what we have is we have 12 to work with, and then we cut off 3 x's. And then each top and bottom are going to be identical, so we're going to divide it, what's left over, in half. And so the length, width, and height, the volume of this thing is 10 minus 2x times 12 minus 3x over 2, and then the height is going to be x. And so it'd be the same procedure. If you want to find the maximum volume, you type that in, you find the maximum on Desmos or in your graphing calculator, and then you'd have what your optimal x cutout would be, and you'd have the maximum volume of this. One other closed type box we might see is very, very similar to this one. It would look kind of like this, but you notice that I've got I've got one more x cut out. So let's once again call this 12 and 10. And so what's going to happen here is we're going to have the same thing. This is going to be the bottom and the top. This is going to be the back, but then the front is going to be both of these flaps folded on top of each other. Really the best thing you could possibly do is just grab a piece of paper, an 8.5 by 11 piece of paper, and cut out these corners. Do exactly this. Like if you wanted to do this box here, what I would do is I would just make a very light crease right down the middle here, and then just cut out the same size square on each side of that crease, and then the same size square out of each corner. You know, do your best to estimate it, and then fold it up and see what you get. I'm going to undo some of these to tidy this up a little bit. But I would encourage you, if you're struggling to understand how this works, if you're struggling to see the spatial manipulation of this shape, actually do it. Grab a scissors and a piece of paper and cut it up and see what it looks like. So the front is going to be x and x, and so the height is going to be 2x for this one, because when I cut off an x off of the front here, don't need that, and an x off of the other flap up here, those two butt up next to each other, and so you're really going to have kind of like a crease, or actually not a crease, but a break in the paper, but they're going to kind of be sitting right on top of each other. And so we would also cut out 2 x's off the back as well. So what do we got? We've got 10 minus 2x for the length here. Same thing, that hasn't changed. But this time we've got 12 minus 4x. We cut off 1, 2, 3, 4 x's off of that 12 side, and then we divide it by 2. So the volume of this box, we would use the expression 2x times 10 minus 2x times 12 minus 4x over 2. If you rewrote this last one as 6 minus 2x, that would be just fine. It's the same thing. So a little bit long-winded on this video, but all of these different types of boxes might be things that you might encounter with optimization. Now, if you're a calculus student, you might be looking at this saying, well, I don't need a graphing calculator, I can use derivatives. If you're not, you'll learn that once you get to calc. But these are 3 different examples of boxes by cutting out corners and folding them up.